Hey everyone, welcome back to Abstract Algebra 1. This will be lecture 7 of the course, and in this section we're going to talk about a new kind of group, the one that we haven't seen before. Well, actually we have seen it, and we'll see how we've seen it. But this type of group we're going to look at is called permutation groups. So let's go ahead and jump into it. Okay, we'll call this section 2.5, permutation groups. And to begin the section, let's start with a definition of a permutation followed by a definition of a permutation group. So a permutation of a set A is a function from A to itself, from A to A, that is both one-to-one and onto. Okay, so you got a set A, maybe the numbers 1 through 5. A permutation of that set is going to be a function from A to itself that is both one-to-one and onto. So meaning meaning everything in the domain in the set A maps to something else in the set A, right? So everything in the set A maps to something in set A, and everything maps to exactly one thing in set A. Okay, so one-to-one means everything maps to one other thing, not to two things. And onto, of course, means everything in A is mapped into, right? So there's nothing left out of the mapping. Okay, so that's what we mean by a permutation. We'll see a bunch of examples in a second. Let's throw out the idea of a permutation group in the same definition. A permutation group of a set A the permutation group of a set A is a set of permutations of A that forms a group. It forms a group under function composition. We'll see an example here in a second. Under function composition. All right. So a permutation is a function that's one-to-one and onto itself, and a permutation group is a set of permutations on this set A that is itself a group under function composition. So you may be thinking back to the dihedral group from our initial section 2.1 of group theory. Our dihedral group is an example of this type of thing, right? There we had different orientations of the square, and those orientations we could combine, we could compose different orientations to get new orientations. But what we saw was that all of those permutations and symmetries of the square were closed, and they formed a group. We had an identity element, we had inverses, and all of that jazz. Okay, so let's see an example here of a permutation group. So we'll just let A equal the sets of integers 1 through 4. Okay. And we'll define the permutation as alpha of 1 is equal to 2, alpha of 2 is equal to 3, alpha of 3 is equal to 1, and alpha of 4 is equal to 4. Now, what does this mean here? So I've got set 1 through 4, and I've defined a permutation, right? And I'm just going to say a permutation here. Right? Because there could be lots of different ones. This is one of them. Right? So in this permutation, this is strictly speaking using the function notation, right? So alpha is the permutation function. So alpha takes the element 1 and puts it in the position of 2. Takes the character 2, the symbol 2, and puts it in the position of 3. 3 goes to 1, 4 goes to 4. 4 stays fixed, we say. right? Because it doesn't actually move, right? So this is a way to notate permutations. It's not a very good way, though. We'll see a couple of different examples of ways to permute or to notate permutations. And this is probably like the least desirable. It's simply because it's cumbersome and it's hard to work with. Okay, but the idea is here, right? This is going to bridge that gap here where we started with the idea of a permutation being a function from A to A, right? So we start with all the elements of A, plug them into this function called alpha, and it maps onto A, right? So you'll notice everything here is 1, 2, 3, and 4. Everything is captured. Everything in A is mapped onto. It's also 1 to 1, so 1 just goes to 2. It doesn't go to 2 and 3 or something like that, right? So 1 goes to 2, 2 goes to 3, 3 goes to 1, 4 goes to 4, right? So it's onto 1 to 1. Okay. Now, this we start with this notation simply to reinforce the idea that a permutation is a function, which is kind of a new idea, perhaps. But a more convenient way to express a permutation would be to use an array. So a more convenient notation involves using an array. Right, so in this case, the array will set it up like this. We'll have the upper row be the j entry, so the 1, the 2, the 3, the 4, and then the lower row be the alpha j entries. Right, so the 2, the 3, the 1, and the 4. So in this notation, this permutation up here would be written as 1, 2, 3, 4 at the top. Always put those in order. There's no reason not to. And then we see that 1 goes to 2, 2 goes to 3, 3 goes to 1, and 4 is fixed. 4 goes to 4. Okay, so this would be a somewhat more desirable way to write permutations. Okay, so let's see another example. Just to make sure we can encode these things. So let's let A be the set 1 through 6. Okay, and we'll define a notation, a permutation gamma. So gamma 1 is 5, gamma 2 we'll say is 3, gamma 3 is 1, gamma 4 is 6, gamma 5 is 2, and gamma 6 is 4. Okay, so we'll say that's our permutation. And so again, we can write the permutation using j up top and gamma j down below. And so we would say 1, 2, 3, 4, 5, 6. Now where's everything go? 1 goes to 5, 2 goes to 3, 3 goes to 1, 4 goes to 6, 5 goes to 2, and 6 goes to 4. Okay, so that would be a slightly more convenient way to write this permutation. Now, what we'll want to be able to do, what we'll need to be able to do is multiply, i.e. compose these permutations. Okay, so let's talk about how that's done using this sort of notation. How to compose permutations. Right, and the emphasis here is going to be on this, using this notation, right? But we'll see another kind of notation which is even better. We're kind of easing into it though, just to see that there are options here, right? So the key thing when we're composing permutations is to keep in mind that the notation needs to be carried out from the right to the left. Okay, so it goes from right to left, and then also from top to bottom. So it's kind of backwards from the way you think about it, like reading or something. And so let's do an example here. Let's see how this can be how we can think of this. So let's let A be the set 1 through 5. And I'm going to define sigma. And sigma will be, let's see, 1, 2, 3, 4, 5. And so it'll map 2, 4, 3, 5, 1. And then separately we'll have gamma. And gamma will map 5, 4, 1, 2, 3. Okay, so I've got two separate permutations on this set A. So what is gamma sigma then? Well, you can think of it like this. So here's gamma. Let's write it in here. 1, 2, 3, 4, 5. 5, 4, 1, 2, 3. And then separately, you've got sigma here. 1, 2, 3, 4, 5. 2, 4, 3, 5, 1. Okay, so if I want to know what these two permutations together are equivalent to, I can think of it like this. 1, 2, 3, 4, 5. So I say, what happens with 1? Well, 1 goes to 2, right? And what happens to 2? 2 goes to 4. So 1 goes to 4. What about 2? Well, 2 goes to 4, 4 goes to 2. What happens with 3? 3 goes to 3. 3's fixed. Oh, sorry. 3 goes to 3, and then 3 goes to 1. Sorry about that. So it's fixed here in this permutation. But so it stays put here, and then as soon as we apply gamma, it moves it. So 3 goes to 3, and then the 3 goes to 1. What about 4? 4 goes to 5. 5 goes to 3. And what about the 5? 5 goes to 1, and then 1 goes to 5. Okay, so gamma sigma here is this permutation, right? So when we compose those two, we get this new permutation. Okay, so for example, gamma sigma of 1, okay, so we started here, we started with the 1, was equal to gamma of sigma 1. Now remember, this guy's sigma here, right? And so sigma of 1 is 2. Right? And then we come over to gamma, which is this other one, and gamma of 2 is 4. Okay, so gamma sigma of 1 is 4. Okay, so this is some pretty basic notation. It's good for getting started with this, though. It helps you to kind of keep things pieced together. It's also not terribly inconvenient to use. It's not too bad to use. There's a better notation that we'll get to in a moment, but it's good to start with this because the thing I like about this is that it keeps the elements listed up above here and tells you exactly where they're going. Right? It's a little cumbersome to write. It's certainly not as economic as other notations in that you have to keep writing 1, 2, 3, 4, 5 every time you write the permutation down. But what we'll see is in a second we can drop that and think of it in a slightly different way and we get a little better results. But let's start with this though. It's kind of easing into it. Let's take a look at some examples of permutation groups. Okay, let's take a look at a couple of examples here. Okay, so we'll start with S3. So we're going to let S3 denote the set of all one-to-one functions from 1, 2, and 3 onto itself. Okay, now so basically what we're talking about is a mapping similar to what we saw above, where 1 goes to something, 2 goes to something, 3 goes to something. And then another mapping where 1 goes to something different, 2 goes to something different, 3 goes to something. Right? Okay, and so this is what we mean by S3. So S3 is a group under function composition. Okay. Now it turns out that there are 6 elements of S3. Okay, there's 6 elements of S3. And let me see here. Let's stick to a good notation here. Yeah, I'm gonna keep it simple. We're not gonna do that. So S3 has 6 elements, and these are basically all the elements of all the different permutations of the numbers 1, 2, and 3. And so I'm going to denote them simply as just alpha 1 through alpha 6. So alpha 1 looks like this. So 1, 2, and 3 map to themselves. This is the identity element. Okay. Alpha 2 is 1, 2, and 3. Now 1 goes to 2, 2 goes to 3, and 3 goes to 1. So it would map like this, 2, 3, 1. Alpha 3 is the element that takes 1 to 3, 2 to 1, and 3 to 2. So 3, 1, 2. Okay. So you can think of these two as being kind of related to one another. So this one, we're kind of shifting everything this way, and then the 1, of course, wraps around. And in this one, these two are similar, but this is a cycle in the other direction. Right? So 1 goes to, 1 is kind of shifting over, 2 is shifting over, 3 is shifting over. Here, that's shifting in the other direction. Now, alpha 4 is the remaining 3 is where we start to fix characters. So in the first one, we fixed the 1. So 1 doesn't move, but the others do. They are going to basically switch spots. In alpha 3, we're going to do the same thing, except we're going to make 3 sit still. Okay, so these guys are basically switching, right? Okay, and then in alpha 4, we're going to make the middle ones sit still. So 1, 2, 3, 2 is in the middle. So this will be 3, and that'll be 1. Okay, so that's all the options. There are no other additional ways to do this. Okay. Now, so those are the elements of S3. Okay, those are the elements of S3. Now we can start to compose some of these guys and see some interesting things. So the first thing to notice is the question of whether or not S3 is a commutative or abelian group. So let's take 2 elements. Let's take alpha 4 and alpha 2. Okay, let's kind of figure out what those are together. Okay, so alpha 4, remember, is this guy, 1, 3, 2, 3, 2. Alpha 2 is this guy, 2, 3, 1, 2, 3, 1. Right, and so what happens when we permute this? So for the 1, 1 goes to 2, and 2 goes to 3. So 1 goes to 2, 2 goes to 3. What happens with 2? 2 goes to 3, 3 goes to 2. What happens with the 3? 3 goes to 1, 1 goes to 1. Okay, so that's alpha 4, alpha 2 when we combine those. Now what happens when we switch the order? Let's look at alpha 2, alpha 4. Alright, so just kind of taking this one and putting it first, and then this one and putting it second. Okay, so 1, 2, 3, what happens? So 1 goes to 1, 1 goes to 2. So already they're different. Right, what about 2? 2 goes to 3, 3 goes to 1. And what about 3? 3 goes to 2, 2 goes to 3. Right, so here you've got 2, 1, 3, here you've got a 3, 1, 2. So these are not equal. Okay, so S3 is not an abelian group. right? So, I mean, an abelian group, remember, is a commutative group. Every element commutes with every other element. And so if you can find a counterexample, then your group is not abelian. And so here's a counterexample. Okay. Now, a lot of what you can do with abelian group, or sorry, with permutation groups is you don't always have to resort to the permutation notation. A lot of times, if you know what the elements are, you can start to algebraically manipulate them, right? And so here's an example. Let's notice something. Notice that, so if I have alpha 2 squared times alpha 4, right? If I do that, so this is like alpha 2 twice, right? So it's this guy twice. Oops, sorry about that. Let me bring this up here. That one. So alpha 2 twice. So alpha 2 is this 2, 3, 1. So 2, 3, 1. So we'll do that twice. And then alpha 4, which is the 1, 3, 2. Now what happens here? So starting with the 1, 1 goes to 1, which goes to 2, which goes to 3. Okay, so I get the 3. And 2 goes to 3, which goes to 1, which goes to 2. Okay, and then the 3 goes to 2, 2 goes to 3, 3 goes to 1. Okay. And so what we can see from this is that alpha 2 squared times alpha 4 is equal to alpha 4 alpha 2. Right? So alpha 2 squared times alpha 4 is equal to alpha 4 alpha 2. Okay. And so if you have identities like this, we can start to calculate other identities without using, having to resort to using the arrays, the permutation notation. So for example, so we can use this, we can use these types of things to derive other identities, right? So with permutation groups, you can figure out some of the algebra, and you can start to discover new things within the group using just the identities and the algebra. So here's an example. If I take alpha 4 and alpha 2 squared, right? So I can say that that is alpha 4 and then alpha 2 alpha 2, right? And that's alpha 4 alpha 2 times alpha 2. Okay, now alpha 4 alpha 2, right? That's this thing, right? And so that's going to be alpha 2 squared alpha 4. All right, so here we're using that identity. Times alpha 2. Let's not forget the alpha 2. So hold on, alpha 2. All right, so just this piece of it is the alpha 2 squared alpha 2 4. Okay, and so then what can we do next? Well, we can kind of organize this a little differently. So I've got alpha 2 squared here, and then let's put the alpha 4 and the alpha 2 together over here. Right, and then that's another alpha 4 alpha 2, right? So I can do the same thing here. I can write this as alpha 2 squared alpha 4. Like so. Okay, and now notice that I've got alpha 2 squared, so that's really alpha 2 to the 4th, and then alpha 4. Okay, and something that we'll see here, I'll whip this out in a second, but this alpha 2 to the 4th is actually just alpha 2. Okay, now why is that? Well, this is a property that we'll discover, or we'll discuss in a moment, but these things start to repeat themselves. Right? There's sort of a cyclic thing, and also there is this idea of an order to each of the elements, right? And so if it turns out, if I take this particular permutation alpha 2, and I roll it over itself 4 times, then I get back to the original, right? And so we can see that 1, 2, 3, and then what is it? 2, 3, 1, 2, 3, 1. Right, if I want to know what that's equal to, well, starting with the 1, 1 goes to 2, 2 goes to 3, 3 goes to 1, 1 goes to 2. What happens to the 2? 2 goes to 3, 3 goes to 1, 1 goes to 2, 2 goes to 3. Right? And then, of course, the 3, 3 goes to 1, 1 goes to 2, 2 goes to 3, 3 goes to 1. Right? And so it's the same. So this here is alpha 2 to the 4th, and this is just alpha 2. Right? And so you can see these types of identities can be derived like this. Okay. All right, so this is just kind of warm-up. We're just kind of getting warmed up, messing around with some of the permutations and some of the different ways we can notate and think about this stuff. Let's take another example. So kind of more, so we've talked about S3. Let's kind of get a little more general. So in this example, let's let A be the set 1, 2, ... up to n. Okay. The set of all permutations of A is called the symmetric group of degree n. The symmetric group of degree n. Okay. It is denoted, how do we denote it? Well, this is Sn, right? We looked at S3, this is Sn. Okay, and so the elements of Sn are these alphas. So you'll have 1, 2, 3, ... up to n. And then you'll have whatever alpha of 1 is, alpha of 2, alpha of 3, alpha of n. Those are the elements, right? These are the elements of the group Sn, right? So don't make the mistake of thinking that these are the elements of the group. These are just the numbers that exist in the arrays, right? The arrays consist of all these numbers, and all of the different arrays are the actual elements. So the arrays / permutations are the elements of the group Sn. Okay. All right, so just a little caution there. So given this group Sn, how many elements are in Sn? So what is the order of Sn? Well, we can think about this. Well, I'll tell you what it is, and then I'll tell you how you can think about it to see that this is obviously true. The order of Sn is equal to whatever n is times n minus 1 times n minus 2 times ... times 3 times 2 times 1. All right, otherwise known as n factorial. Okay, now why is that? Why is that? You know, is it obvious? Why? For people who have been through maybe a combinatorics class, or maybe have taken some statistics, or you may have encountered something like this. You may have seen something like for example, in statistics, when you're learning probability theory, you talk about how to permute objects. You have to learn how to count in a combinatorial way in order to calculate the number of elements in a sample space frequently. That's the main application that you come across, right? But the way to think about it is, if you think about having a permutation, right? In the first position, there's n items in A, so you have n options for the first position, n choices. All right, the second position, Well, one of the choices is already taken, right? So you've got an element here now, and so how many can you choose from here? N minus 1 choices, right? N minus 2 choices. Until finally down here you have 2 choices, and then you have 1 choice. Well, that's exactly what we're talking about up above here, right? Right, so if I put 10 here, then I've got, you know, N minus 1 choices. Maybe I put a 17 there. And then I've got, these 2 are taken, I've got a N minus 2 options. I put 3 there, right? And so on, whatever. So that's the idea, right? You kind of, you can build up the permutations using this factorial language. Okay, and so the order of Sn is n factorial. We'll come back to Sn in a minute. We'll use it throughout this section. It's extremely, it is the sort of, it is the perfect example for permutation groups. It's the best example. Let's take a look at, let's revisit the dihedral group. Okay, the dihedral group, D4. The dihedral group. You can think of the dihedral group, I mean, we didn't think of it at the time, but you can think of the dihedral group as a permutation group. It's actually more convenient, in my opinion, to think of it as a permutation group. So think about your square here. Let's label. Before, previously when we talked about this, we had the corners labeled by colors, but let's label them by numbers. So we'll put 1, 2, 3, and 4, right, to denote the corners. If you recall, there was a 90-degree rotation element in the dihedral group. We called it R90. Right, and so what does that do? Well, 1 goes from here up to here, right? So let's draw it. 2 goes, you know, everything moves 90 degrees counterclockwise, so 2 goes over here. 3 goes down here, and then this becomes 4. Well, you could denote this as a permutation. So what happened to 1? 1 went to 2, right? So 1 went to 2, right? It kind of slid up here. It took 2's place. What happened to 2? 2 went to where 3 is. What happened to 3? Well, 3 started out here, and then it moved down here. So it went to 4, and 4 went to 1. So R90 is equivalent to this permutation. Okay, another example. So if I start 1, 2, 3, 4, and I think about like a vertical flip. So remember, this is where you flip the paper over along this vertical axis, right? So it's like a rotation like that. Not 360 degrees, but a half rotation, right? And we'll call this a V for a vertical flip. All right, what happens to all the elements? 2 goes to 3, right? So 2 and 3 switch places. And 1 and 4 switch places, don't they? Maybe I'll give it a different name altogether. How you name these things is sort of open. So 1, 2, 3, 4. Okay. And so in this case, 1 went where 4 is, right? So 1 and 4 switched spots. So this became a 4, and that became a 1. And 2 and 3 switched spots, right? So this is a 3, and this is a 2. Okay. All right. And so these are really just permutations on S4, actually, right? So when you think about D4 in this way, using permutations, you kind of realize that D4 is actually a subgroup of S4. So it turns out that D4 is a subgroup of S4. Now remember, S4 has how many? It's 4 factorial. How many elements in S4? So it's 4 factorial, so that means there's 24 elements. Okay. And we know that D4, because we've went through it, you know, very closely in an in-depth couple sections back, D4 had exactly 8 elements. right? So if you take 8 of the elements in S4, they form a subgroup called D4, right? So this dihedral symmetries of the square is actually a subgroup of this permutation group called S4. So things are starting to kind of build a little bit, aren't they? Okay, all right, very good. Let's keep moving. Now we're going to switch notations a third time, and this is the notation that we'll want to land on, I think, in general. Like when we're reasoning about the elements of a permutation group, we'll want to probably use what's called cycle notation. Another notation, notation is called cycle notation. Okay, and it is it's the best of the notations we've looked at. Well, meaning that it's better than the one we just looked at, the array notation. So let's take an example. We'll kind of break it down. How does this work? So let's consider some permutation in S6. So 1, 2, 3, 4, 5, 6. Okay, and this is the array notation. It would be 2, 1, 4, 6, 5, 3. Now, let's think about what actually happens here. Let's kind of draw a picture. Picture what is happening. Okay, so 1 is going to 1 and 2 are switching places. You can see 1 goes to 2 and 2 goes to 1, right? So there's a switching of places happening here. So I've got the element 1 and the element 2, right? Now alpha takes 1 and puts it at 2. And see that 1 goes to 2, and it takes 2 and puts it at 1. So there's like this rotation happening between 1 and 2. Right? That's this piece of it. Now notice 1 and 2 don't have anything to do with these guys over here. Whatever's happening with 1 and 2, these guys over here are in their own little world. Well, 1 and 2 are in their own little world, we'll say. Now something else we notice here is that 5 is staying put. It's fixed. Right? So the 5, what does alpha do to 5? It just takes it and puts it right back where it found it. Right, so that's this piece. Okay. So 1 and 2 are kind of oscillating between each other. 5 is never moving. And then 3, 4, and 6 are moving amongst themselves as well. They're kind of mixing, aren't they? So we'll write it like this. We'll put the 3 up here, and then we'll put the 4 over here, and then the 6. So notice 3 goes to 4. Alpha takes 3 to 4. And then what happens to 4? 4 goes to 6. So alpha is moving 4 over to 6. And then 6 is going back to 3. Remember, this is always alpha that's doing this, right? Alpha maps these things in this way. Right, and so you've got separately those guys there. Right, so you kind of have these little compartmentalized areas of interaction. 1 and 2 are interacting, 5 is separated out, and 3, 4, and 6 are interacting. Right? So this kind of thing can be expressed in an economic way using cycle notation. Right? So this can be expressed using the following notation. So alpha, we'll say, is equal to 1 and 2 in a cycle, 3, 4, and 6 in a cycle, and 5 by itself. Okay. Okay. Right, so this is how you would break it down. You would say 1 goes to 2, 2 goes to 1. So the way you would think about it here is 1 goes to 2, and then 2 goes back to 1. So it's kind of like you'd read it from left to right. This one goes to this one, and then when you get to the end, it goes back to the beginning. So here with the 3, 4, 6, 3 goes to 4, 3 goes to 4, 4 goes to 6, 4 goes to 6, and 6 goes to 3. Right, see how it's a circle? 3, 4, 6, 3, 3, 4, 6, 3, 4, 6, 3, right? So it kind of wraps around. 3 goes to 4, 4 goes to 6, 6 goes to 3. And then the 5's all by itself. 5 goes to 5, 5 goes to 5. It never moves. Right? So 1 goes to 2, goes to 1, goes to 2, 3 goes to 4, goes to 6, goes to 3, 5 stays put. Okay, let's do another example. Make sure we can transition between these two kinds of notation. So let's write beta, again, a S6 element. 1, 2, 3, 4, 5, 6. So 5, 3, 1, 6, 2, 4. 5, 3, 1, 6, 2, 4. Okay, and let's write beta in cycle notation. So what's going on with 1? 1 goes to 5. What happens to 5? 5 goes to 2. What happens to 2? 2 goes to 3. What happens to 3? 3 goes back to 1. And it starts over again. Okay. So that's a cycle within this permutation. Now, what the convention is to go to the next number higher that isn't included. So I've got 1, 2, 3. I don't have 4, so let's start with 4. Okay, what happens to 4? 4 goes to 6, and 6 goes to 4. Okay. There it is, right? So I can write it really quickly and simply like that. Okay. And so just to recap what we did with that same thing, let's do it again with alpha here, because we're going to use them in an example. So I had 1, 2, 3, 4, 5, 6. And then 2, 1, 4, 6, 5, 3. 2, 1, 4, 6, 5, 3. Okay, and so alpha, we'll start with 1. 1 goes to 2, and 2 goes to 1, so that closes that cycle. What about 3? 3 goes to 4, 4 goes to 6, 6 goes to 3, so we close that cycle. And then 5, well, 5 goes to 5. Right, so it's just that it's that simple to write these out. Okay. Very good, very good. Okay. All right. Let's see here. What happens next? Let's see. What if we want to multiply? What if we want to multiply things together using cycle notation? Okay. Let's see an example. So I'll start with the array notation. Let's say my alpha is in S5, so 1, 2, 3, 4, 5, and then 2, 1, 3, 5, 4 is the permutation. And then let's say I've got a beta also in S5, and it's 5, 4, 1, 2, 3. So first let's convert this to cycle notation. Right, so we'll start with the 1. 1 goes to 2, 2 goes to 1, so 1, 2. And then the 3 goes to 3, it's fixed. And then 4 goes to 5, 5 goes to 4. Okay. And for the beta, we've got 1 goes to 5, 5 goes to 3, 3 goes back to 1. What about the 2? 2 goes to 4, 4 goes to 2, and that's it. 1, 2, 3, 4, 5. Yep. So we've got our alpha and we've got our beta. So if I want to multiply these together, well, if I want to write down the element alpha beta, it's going to be in S5, whatever it happens to be. Let's write it down. So of course I could write it like this. 1, 2, 3, 4, 5, 1, 5, 3, 2, 4. Now, this isn't wrong, but it's kind of like writing the fraction 100 over 10, right? It's like most of the time you wouldn't want to express it that way. It's a little cumbersome, a little inconvenient. This is what's called the way we have this written, it's called not disjoint. Right? The reason it's not disjoint is because, for example, I've got a 2 here, and I've also got it listed over here. Right, so there's some redundancy. I've got a 3 and a 3. I've got a 5 and a 5, a 1 and a 1, a 4 and a 4, right? So there's some redundancy here. So what I should do is I should sweep through this and reduce it. And that's a very simple thing to do. You just kind of go through it. So remember reading from right to left. So the 1 is here. 1 goes to 5. 5 goes to 4. Now what happens to 4? 4 goes to 2. 2 goes to 1, right? So I'd wrap around here. And let's see what happens with 2. 2 goes to 4. 4 goes to 5. And what happens with the 5? 5 goes to 3. 3 is fixed. Okay. And then what happens with the 3? Well, 3 goes to 1. And 1 goes to 2, so it wraps around, doesn't it? Okay, and so this would be an example of writing alpha beta in a disjoint, as a disjoint permutation. That's generally how you want to do it. You want to think of disjoint permutation, writing a permutation as a disjoint permutation. That's sort of like reducing a fraction. It's preferable. It's easier to look at, easier to deal with. Okay? It's simplified. Right? When I plug in 1 to alpha beta, I don't have to look at this and figure out how it's all going to work out. I can just look at here and go, oh, it's going to go right to 4. Right here, I'd have to say if I plug in a 1, it goes to 5 first, and then it goes to 4. Okay, it's an extra step. So this is like a simplified, reduced version of this longer version. Okay, perfect. Let's see. I think this would be a good place to. Well, actually, in a moment, I'm going to pause the video. But let's let's do a couple theorems related. So we're going to jump now to properties of permutations. And of course, this is properties of permutations in the context of group theory, permutation groups, right? So the first one is, some of these we will prove, some of them we will not. This first one we're not going to prove. Just have to take my word for it. Every permutation of a finite set can be written as a cycle or as a product of disjoint cycles. So every permutation of a finite set can be written as a cycle or as a product of disjoint cycles. Okay, and so this is what we've been up to, right? So when we say it can be written as a cycle, we mean it like this. This is an example of a cycle. 1, 2, 3, 2, 4. This would be an example of a cycle, not disjoint. And then 1, 2, 3, 4, 5. This would be an example of a disjoint cycle. So what this is saying is that every permutation of a finite set, basically any n elements that we want to permute, create a group out of, it can always be represented as this, ideally, or in the cases like what we've seen, this, a product of disjoint cycles. Right? There's no need for any element of any permutation group to ever be written as a non-disjoint cycle, product of non-disjoint cycles. Okay, you can always simplify it down so that it's disjoint. That's what the first theorem says, which is nice. Okay. All right. Very good, very good. Let's see here. I'm trying to think. Yeah. Let's do one more theorem, and then we'll write a proof of that theorem, and then we'll break. So this theorem, related. So this theorem says if the pair of cycles, so if I've got a pair of cycles, alpha, which is A1 through AM, we'll say, and beta, which we'll say is B1 through Bn, have no entries in common, right? Meaning they're disjoint, right? They have no entries in common, meaning if there's a 2 over here, then there isn't a 2 here. If there's a 10 here, there's not a 10 there, right? So if these two cycles, alpha and beta, have no entries in common, then alpha beta equals beta alpha. They commute. Okay, so they commute. So if two cycles have nothing in common, they commute. And so all of the examples that we saw, all disjoint cycles are basically able to commute, right? All of the examples that we've looked at, whenever they're disjoint, you can swap the order. Okay. All right, let's prove this theorem. Okay, let's prove this one. Let's say that alpha and beta are permutations. So let's say that alpha and beta are permutations of the set, and we'll say the set is S, and just, to kind of level set here, we'll say we've got A1 through AM, B1 through Bn, and then we've got some extras in here, C1 through CK. Okay, and so here the C1 through CK are the members of S that are left fixed by both alpha and beta. So they're the elements that are left fixed by alpha and beta, right? So alpha and beta, those cycles, they don't move any of the C's elements. They're just kind of stuck there. Okay. Now, in order to show that alpha beta equals beta alpha, what do we need to show? Well, we wish to show that alpha beta of x equals beta alpha of x, and this needs to be true for all x and s. Right, so. Okay, now there's really three options here, right? Either your x can be one of the a's, or it can be one of the b's, or it can be one of the c's, right? And all three options, even without me writing it out, you can probably imagine what's going to happen here, right? Let's take it one by one. So we'll say first, if x is one of the a elements, we'll say AI. Then what happens? Well, I've got alpha, beta times AI, right? So that's equal to alpha times beta of AI. Okay. Now, beta doesn't have, AI is not in the beta cycle, right? Remember, by assumption up here, right? So remember, it says alpha and beta have no entries in common, right? So that means AI is one of these, so it's not one of these, right? So that means beta doesn't do anything to it, right? So this is just alpha of AI. Okay, and now alpha is going to do something to it, and what we'll say it does is it moves it forward in the cycle. That's what happens in the cycle, right? It moves. So if it's AI, then alpha pushes it forward, right? Remember how the cycles work? If I have 1, 2, 3, so if this is AI, 2 goes to 3, right? So AI goes to, oops, I didn't mean to write it like that. I meant to write it like this. AI goes to AI plus 1. Right, so it just moves it forward. All right. What happens with beta alpha? Right, beta alpha of AI, well, let's see. So again, that's going to be beta times alpha of AI. Alpha of AI is going to, again, move it forward. So now I've got beta of AI plus 1, like so. And now, again, this is one of the A's, so it's in the A cycle, meaning it's not affected by B or by beta, right? And so that means it's AI plus 1. And they're equal. So alpha beta equals beta alpha in the case of X being one of the A elements. All right. So hopefully that's straightforward, right? The key here is to really understand what it means when it says here that alpha and beta have no entries in common, right? So what that basically means is that if an element is moved by alpha, then it's unmoved by beta. Basically, if it's moved by beta, then it's unmoved by alpha. Okay, and so that's what this whole argument depends on. All right, the reason the AI here stays AI is because beta can't move it. And the reason the AI plus 1 stays AI plus 1 here is because the beta can't move it, because it's one of the A elements. Now, you could obviously make the exact same argument for X being one of the BI, right? So the same argument can be made for X being one of the B elements, right? So just like up here where we could see alpha beta equals beta alpha, the same exact argument could be applied here to show that alpha beta equals beta alpha. Okay, so it's fine. It's straightforward in the cases of X being one of the A's or X being one of the B's, and it's actually even more straightforward if X is one of the C's. So remember, the C elements are the elements that are unmoved by alpha or beta, right? So then I've got alpha beta of some C. Well, that's equal to alpha beta of Ci. Well, beta doesn't move Ci, so that's alpha of Ci. Alpha doesn't move Ci either, so it's just Ci. Now, obviously, if I switch the order of alpha and beta, it's not going to change anything here, is it? No. Alpha of Ci, alpha doesn't touch Ci, so it's just Ci. Beta doesn't touch Ci, so it's just Ci. Okay, and so that's the whole proof. Alpha beta equals beta alpha. Okay, very good. All right, so disjoint cycles commute with one another. Right? If you got a disjoint cycle, you can switch it around. You can change the order. Doesn't matter. Okay. All right. Very good. Let's see here. Okay. Let's go ahead and end the video here, and we'll come back with a part B, where we'll pick it up right where we left off here. So, all right, we'll go ahead and end here, and we'll come right back.